You written exams? Hello.
Good, sir.
Yeah, fine. See, last class already we started the applications of OPAMP. Just 5 minutes I will rewind the topic and next I go to the remaining part of the applications. So first basic application of your OPAMP is inverting amplifier. See, if you observe this diagram, this is the basic OPAMP. Here, this is the inverting terminal, we know that, and this is the non-inverting terminal. So applying the input at inverting terminal, that's why we call it as inverting amplifier and output. So what there is a concept called virtual ground concept. We are applying that virtual ground concept from this. For ideal op amp, open loop voltage gain AOL is equal to infinity. And we are writing the equation for AOL is output voltage by differential input voltage. Okay, differential input voltage means let us take voltage at this point is V1, voltage at this point is V2. Now we can write VD is equal to V2 minus V1. Now if I substitute that one here, P naught output voltage by VD means V2 minus V1 is infinity. The meaning of this one is V2 minus V1 equal to 0 from this. So it means V1 equal to V2. So whenever your op amp is open circuited, if you take op amp like this, not open circuited, we apply that one from AOL is open loop voltage gain. This is negative, it is positive, and we are saying it as V1, it is V2. This is output. Now you can write directly. So whatever the voltage here you have, here also same voltage. So between 2 points, if you want to maintain a same voltage, those 2 points should be short circuited. Then only you can maintain same voltage. So practically these two are not short circuiting, but even though both are maintaining same voltage. That's why we call it as virtual short circuit concept. So with respect to that concept, so once this non-inverting terminal is connected to ground, that means 0 volts. So whatever the voltage here, it should maintain the voltage at this point also maintain the same value. So both are seems to be short circuited. So virtually short circuited, physically not short circuit, virtually short circuit. So that's why voltage here is 0 volts. Now, and the currents entering into the op amp terminals is 0. Already we know that. Okay. Now let us take this current is I1, this current is I2. Now, if you apply KCL at this node, I1 is entering, I2 is leaving, and this is the 0 amps. Current entering into op amp. Now I1 equal to 0 plus I2. Okay. So here I explain I1 is equal to I2 plus 0. Now I1 is written as Vi minus 0 by R1. So now I2 is 0 minus V output by RF. So I'm going to equating I1 equal to I2 from this equation. So by substituting the values in this, we got output is equal to minus RF by R1 into Vi. This RF by R1 is called as closed loop gain or closed loop voltage gain. The negative symbol here represents the 180 degrees phase shifted output compared to input. Output is phase shifted by 180 degrees. So here you have to clearly represent the value of the gain of its closed loop gain. ACL is minus RF by R1. Okay, so that is inverting. Now I'm going to the second application, non-inverting. In non-inverting amplifier, input is connected at the positive input terminal, that is non-inverting input terminal. So due to virtual short circuit concept, voltage here also is going to be VI. VI. Now I'm taking the currents. Let us take I1. This current is I2. And apply KCL at this node. Then you get the output. Finally, here you get output voltage is from this. You get output voltage V0 is equal to 1 plus RF by R1 into VI input voltage. That is the output voltage you get. So closed loop gain ACL is V0 by VI. Is V0 by VI. It is equal to 1 plus RF by R1. Please all of you once again write down these equations. For inverting amplifier 1 minus RF by R1. For non-inverting amplifier 1 plus RF by R. Okay. So this is the simplification we done. Next one is in that closed loop. This is the non-inverting amplifier just before we completed. In that, this is the output equation, voltage equation. Now I am taking, this is infinity and RF equal to 0. Infinity means open circuited. It should be open, it is open circuited. Infinity means, and it is 0 means short circuited. Now substituting 1 plus RF is 0, R1 is infinity. So 0 by infinity became 0. So output equal to input. So output voltage just follows the input voltage. So that's why it is called voltage follower. The application of voltage follower is to convert practical voltage source to ideal voltage source. First of all, I will explain what is practical voltage source. See, if you take a voltage source, we are representing the voltage source like this. Let us take V. This is R. This is the terminal voltage. So terminal voltage is V minus I into R. This is the current of I. Now, ideal conditions, we are expecting this terminal voltage equal to the supplied voltage V. But here, our terminal voltage V minus something. You are losing something due to this resistance. So if you take the source IS, VS, RS. Now, I am taking the same voltage source. I am going to be connecting that one here. Let us I am connecting this one here. Now, by connecting that one here, it is RS. And here I am connecting VS. So the output voltage is now written as, see, if you analyze this circuit, the current entering into op amp terminals is 0. Now the drop across this one also 0 volts. So voltage at this point Vi is equal to Vs. Vs. So this is output voltage is nothing but a Vi because it is voltage follower. It is nothing but a Vs. See here Vs minus something, we are losing something. This is practical voltage source. Now we can use this is a ideal voltage source. Ideal voltage source. So this is the one of the best example for voltage follower. Okay, please all of you write down that the application of voltage follower is to convert practical voltage source into ideal voltage source. to convert practical voltage source into ideal voltage source. Into ideal voltage source. So next one is adder. So here we can define classify the adders into two types. Based on the point terminal where you are applying input, you can classify the adders into two types: inverting adder and non-inverting adder. For inverting adder, input is applying at inverting terminal. Inverting terminal. For non-inverting adder, inputs are applying at non-inverting terminal. Okay. Now this is inverting adder. Now I'm applying the same procedure. Okay. So this is the regular procedure. Already we completed that. Now I will explain now simply in a simple way how to write the output equation for this. Now I'm applying superposition theorem. So according to superposition theorem, when multiple sources are acting on a circuit, the response on any terminal is sum of the individual responses caused by the individual sources acting along. So according to that, two sources here we have V1 and V2. So now let us V1 is acting, V2 is non-operative. In that case, output is V01. So in that case, output is, let us take V01. So now once it is active means it is 0 volts. Now it is 0 volts. That means it is grounded. It is 0 due to voltage virtual short circuit concept. Here also 0 volts. 0 volts, 0 volts. No current flowing through that. Current is 0. Current 0 means you can neglect this one. Okay, you can neglect that. Once you are neglecting that, now this is the remaining part of your circuit. This is nothing but your inverting amplifier. Now output is minus RF by R2. RF by R2. Similarly, now I'm going to V02. That is, now this is present, this is grounded. Okay, so in that case, so this is grounded, this is present. Now same one, 0 volts here, the current through this 0, so you can treat it as open circuit. Now this is going to be your final circuit. Final circuit. Now it is again an individual inverting amplifier. Now output voltage is minus RF by R1. So total output is V01 plus V02. So that is minus RF by R1 plus minus RF by R2. Now here I am taking let R1 equal to R2 equal to RF. So this is the condition, R1 equal to R2 equal to RF or R. And RF also I am taking again R. In that case, all will cancel. Now output voltage is, so one more thing, here we have V1, it is V2, it is V1 here we have additionally. V1, it is V2. So output is minus of V1 plus V2. So this is the inverting adder. So even though if you are adding one more R3 and V3, you can add one more here. So now you can add one more plus minus RF by R3 into V3. Like that, if you're adding multiple things, you can add multiple outputs at output equation. That is about inverting adder. Next one is a non-inverting adder. See this non-inverting adder here. See this? In this, now two inputs are applied at signals are applied at non-inverting terminal. Except this, if you verify this part, this is a non-inverting amplifier, we know that. So output voltage is always 1 plus RF by R. 1 and R3, here it is. RF by R3 into, let us take voltage at this point is Vx. Vx. Now we need Vx. This is Vx. So this is nothing but a voltage applying again superposition theorem. Now applying superposition theorem, we can write Vx is, let us, this is activating, this is acting, and this is non-acting. That means it is acting, it is present, it is 0. So V1 into R2 by R1 plus R2 plus, once it is active, it is non-active. So it is V2 into R1 by R1 plus R2. So simply we can write V1 into R2 plus V2 into R1 by R1 plus R2. Okay, now if I am taking R1 equal to R2, both all will cancel. So now take this Vx value, substitute here. Let us, I am assuming all resistors are equal. All resistors are equal. Now it became V1 plus V2 by 2. If all resistors are equal, it became 2Vx. Finally, output voltage is, it is 2Vx. Now it is 2 into Vx is a V1 plus V2 by 2. 2 gets cancelled. Now it is V1 plus V2. Okay, so that is the non-inverting adder. Okay, so this is the procedure. So now I am discussing the same circuit I am taking with the additional resistor. Now I am adding just additional resistor R4 at a non-inverting terminal, which is connected to ground. Students, are you following? Hello? Please respond someone. Are you following, sir? Hello?
Sir.
So no problem? Sir, is it okay? Hello? Hello? Sir, please. Okay, thank you. Now, sorry, see this? Now it is, see, in this circuit, now let us take, this is the voltage Vx. Here voltage is Vx voltage. Now similar to previous case, we can write Vx is, sorry, V output is 1 plus Rf by R3 into Vx. Okay, so see, this is Vx we are taking. Now V output is 1 plus Rf by R3 into Vx. So I want to apply superposition theorem to get the value of Vx. So according to superposition theorem, let us, this is active, this is non-operative. This is active, this is passive. Active means operative, passive means non-operative. Non-operative means connected to ground. Now these two are parallel to each other. Now Vx1, once it is active, equal to V1 into R2 parallel with R4 by R1 plus R2 plus parallel with R4, this one. Similarly, once it is active, Now I'm taking, this is grounded and this is active. Now it is V2 into R1, V2 into V2 into R2 parallel with V2 into R1, sorry, this is grounded, R1 parallel R4 by R1 parallel with R4 plus R2. This is what. Okay. So based on the taking the different values of resistors, you get the relation between input and output. This is the non-inverting. And so now I'm going to subtractor. Okay, subtractor. See, in this, two input signals are applied. One is at inverting terminal, other one is at non-inverting terminal. And these are the equations. RF R1, R2, this is R3. Okay, now I'm following the same procedure. We know that voltage at inverting equal to voltage at non-inverting. So Vx equal to Vy. Let us voltage here Vx we are taking Vy. Now Vx is written as V0 into, say I'm writing Vx equation, sir. V0 into, so that means V output into R1 plus V1 into RF by R1 plus RF. So, similarly, Vy is V2 into R3 by R2 plus R3. Just equate Vx equal to Vy, then you get the relation. Okay, so that was we done here. Now output we got RF by R1 into RF by R1 into V2 minus V1. Okay, RF by R1 into V2 minus V1. This is the subtractor. Now I'm taking adder subtractor. Adder subtractor. This is the adder subtractor circuit. Okay. See, once they given this problem in your exam, first you have to check one thing. The resistors which are connected at inverting terminal, this one, this one, this one. So these three resistors are connected to inverting terminal. Similarly, for non-inverting terminal, these resistors are connected. R4, R3, R4, R5. If this group of resistors equal, similarly, this group of resistors equal. If this group and this group are equal, then you can write output is at positive terminal V3, V4. So V3 plus V4 minus at negative terminal V1, V2, V1 minus V2. That's it. So sorry, V1 plus V2. So that is the output equation. That's it. Resistors are equal. Okay. 10 resistors connected at inverting terminal are equal, and the group of resistors which are connected to non-inverting terminal are equal. Then we can write the output equation is like that: V3 plus V4 minus of V1 plus V2. In previous GATE, IES, in all the competitives, they given one problem. Just go to the problem here. Okay. First, after completion of this part, I go to the problem. See, for example, now they given a problem in exam. Let us different values of resistors. Then what we have to do? Different values, all are different values. Okay. Now, in that case, Just I am following the superposition theorem, not more than. First, let us already be verified. Just check these two. This make these two to ground are V3, V4. Now V1, V2 are present. Once V1, V2 are present to this, sorry, first V1 is active, remaining two are non-active. No current flowing through that, no current flowing through these three, now open circuited. Now with respect to V1 is at inverting terminal, now it is inverting amplifier with respect to V1 minus RF by R1 into V1. So minus RF by R1 into V1. Similarly, so now I am taking the V2 is active. So V2 is active. So with respect to V2 also it is a inverting terminal, inverting amplifier because it is connecting to inverting terminal. No current through this. Now output is minus RF by R2 into V2. So minus RF by R2 into V2 over. Next case, I am taking the next input terminal is active. V3 is active, remaining all are non-active. Okay. So V3 is active. So once it is active, this one connected to ground. Okay. Now once these two are parallel to each other. R3, R4, R5 are parallel to each other. Now output voltage is voltage at this point into, and one more thing, sir. These two also connected to ground. Now once it is grounded, both the terminals are at same potential. Both are parallel, that is R1 parallel with R2. Let us take voltage here is Vx. Now output voltage with respect to V3 is V3 is Vx into 1 plus Rf by, in place of R1 we have R1 parallel with R2. This is the equation. So that was I've written here. 1 plus Rf by R1 parallel with R2. Now we need to measure the voltage Vx. So Vx is nothing but these two are parallel. So V3 into R4 parallel with R5. V3 into R4 parallel with R5 by R3 plus R4 parallel with R5. So that is the voltage with respect to V3. Output voltage. Next, I am taking last one is active. Last one is active. Now V4 is active, remaining. In that case, same thing, same voltage Vx here. Now output is 1 plus Rf by R1 parallel with R2. Parallel with R2 into. Now this is active. Sorry, this is active. So now Vx equal to V4 into R2 parallel with R5. Sorry, this is R3. R3 parallel with R5 by R3 parallel with R5 plus R4. So like that, by seeing problem itself, you can directly write the values in that. Okay. No need to doing the step by step like your semester exam. In semester exam, you get this one for 10 marks. But in GATE, you get hardly for 2 marks. Okay. So the same step I mentioned here. The group of resistors connected here and here are same. Then output is V3 plus V4 minus V2 plus V1. So they are the applications up to there. Now I'm going to, the next application is integrator. So total, now I'm discussing linear negative feedback applications. So all of you please note down the applications of op-amp in negative feedback applications. That too linear negative feedback applications. Similarly, we have non-linear negative feedback applications also is there. Now first write down negative feedback linear applications. First one is inverting amplifier, second a non-inverting amplifier, third one is adder, fourth one is subtractor, fifth one is adder subtractor, sixth one is integrator, seventh one is differentiator, eighth one is voltage to current and current to voltage converter, and the ninth one is instrumentation amplifier. In your exam, in your syllabus, BTech syllabus, all these applications comes under a single unit. Okay. Okay. Now I'm going to integrator. See, this is integrator. Okay. Let us just wait 1 minute. So now what is this circuit? What is this circuit? So I don't know what this circuit is. Previous applications from the knowledge of, yes, sir. Please tell me, sir.
Integrator.
How can you say it is integrated?
Feedback is capacitor.
So what? Once feedback in capacitor, okay. Then what? Okay, I do one thing. If I'm going to replacing this one by inverter, sorry, inductor, I am replacing R1 by inductor. Then, for example, this is my circuit. This is my circuit. RF, L, Vi. Now, what is this circuit? Which circuit it is? Which one, sir?
No idea, sir.
Say, now, to get the idea, you have to deduce a relation between input and output. Based on that relation, you can specify the circuit is belongs to which type. Okay. Now, let us, I am going to verifying this. Let us take this is IL. This is IF. So according to virtual short circuit, voltage here is 0. Applying KCL at this node, IL equal to IF. IL is equal to IF plus 0 current entering into this side. Now IL is equal to current through the inductor. Okay. Current through the inductor is L into di by dt. Sorry, V is equal to L into di by dt. This is the voltage across the inductor. Now if you want current, I is equal to 1 by L into integral V into dt. This is the current through the inductor. Same thing I am applying. IL is equal to 1 by L into integral V means voltage at this point minus voltage at this point. Voltage at this point is Vi minus 0 voltage at this point into dt. Okay, E is equal to IF. IF is equal to 0 minus V output by RF. Now, so this is 1 by L into integral Vi into dt is equal to minus V output by RF. So now V output is written as V output is
Minus RF by L.
minus RF by L into integral Vi dt. So all these are constants. Now, can I write from this? Output is directly proportional to
Integration of Vi.
integral of integrator. What, sir? Because output is directly proportional to integral of input signal. So that is the integrator. Sir, is it okay?
Okay, sir.
So like this, by applying a proper procedure, same procedure, previously what we discussed. Applying a procedure, we can identify the given circuit is a integrator or differentiator. Okay, sir. Now we go and verify our next circuit. Okay, now I'm going to arising this. So this is the procedure.
అంటే సార్ చూడగానే మనం ఏం చెప్పలేము సార్ ఇది ఇంటిగ్రేటర్ అని డైరెక్ట్గా.
సార్ అది ఇంటిగ్రేటర్ అనేది చెప్పొచ్చు, బట్ అలా చెప్పాలంటే ఫస్ట్ యూ హ్యావ్ టు గో ఫర్ ఫిల్టర్స్. వీ హ్యావ్ యాక్టివ్ ఫిల్టర్స్ ఆఫ్టర్ దిస్ టాపిక్. ఓకే, ఇన్ దట్ యాక్టివ్ ఫిల్టర్స్ this integrator is acting as a, already you studied integrator acting as a low pass filter, differentiator acting as a high pass filter, all those things. Yes or no? Hello?
ఫస్ట్ నుంచి చదువుతున్నాం సార్, ఈ చాప్టర్ ఇప్పుడు ఉంది సార్, ఈ సెమిస్టర్లో ఉంది సార్ నాకు.
Okay. So filter అనేది integrator and differentiators acting as a filters also, low pass filter, high pass filter. What is filter? Sir, what is filter?
అంటే మనకి అన్వాంటెడ్ ఫ్రీక్వెన్సీస్ అన్ని వదిలేసి కావాల్సిన ఫ్రీక్వెన్సీస్ అన్నిటిని.
Very good. So filter is a frequency selective circuit. అవునా కదా? Filter is a frequency selective circuit. Okay.
ఓకే సార్.
Now, so first the given circuit you can easily identify it is a low pass filter or high pass filter. Based on the filter type you can decide it is a integrator or differentiator. I will explain that one. For example, the simple method is there. I will explain that simple method to you. So this is the circuit just before we discussed. No. See, already we know one thing. See, for frequency 0, that means low frequency, your capacitor is open circuited and inductor is short circuited. Yes or no? Sir, are you clear about this?
ఎస్ సార్.
Now, similarly, for high frequency, capacitor is short circuit and inductor is open circuit. Yes or no?
ఎస్ సార్.
ఓకే.
Now let us apply f equal to 0 and f equal to infinity on this. First f equal to 0 applying, f equal to infinity applying next. For f equal to 0, so f equal to 0, inductor is short circuit. It is short circuit. Once it is a short circuit, this is resistor is present. Now you are getting some output. So you are getting some output. Yes or no?
ఎస్ సార్.
Next, f equal to infinity, it is open circuit. Open circuit means now it is open circuit. Are you get anything at output?
నో సార్.
Nothing you are getting. So for high frequency, you are not getting anything at output. For low frequency, you are getting something at output. So it allows low frequency component. It blocks or it attenuates high frequency components. So allowing low frequency, so it is called a low pass filter. So integrator is a low pass filter. Now I will test the above circuit. Now I am going to above circuit. See this. Same concept I am applying on this circuit. F equal to 0, f equal to infinity. For f equal to 0, what about this capacitor? Open circuit. It is open circuited. Open circuited. So once it is open circuited, your op amp is enter into open loop mode. Then output is either plus or minus V saturation. Okay, sir.
ఓకే సార్.
Okay. Now, for f equal to infinity, so that means anything, some output you are getting it or not? You are getting some output anyway, whatever it is. For f equal to infinity, your capacitor is short circuited. See, once it is short circuited, so your output is connected to this point, but voltage at this point is 0 volts due to virtual short circuit concept. So your output is 0. So you are not getting anything at this point, but something you are getting at this point. So it is a low pass filter. So already, if anything is low pass filter, that is integrated, acts as an integrator. Sir, is it clear?
Yes, sir.
So this is the shortcut we have. So we discuss in detail about these shortcuts in our active filters topic we have. There we discuss about in detail about that. Because first you have to learn about what is integrator, why we call that as an integrator, frequency plot of it, what is ideal integrator, what is practical integrator, okay, why we are switching, what is the reason to go to practical integrator, why not preferring ideal integrator. So first you should be thorough with all those things, okay. After that we are going to that, and one more we have order of the filter, first order filter, second order filter. Already you know that first order differential equation, second order differential equation, all of you are aware of those orders. Is it there or not? So what is the reason? Why are you going to higher order filters? Why not you are satisfying with first order filter? Why are you going to second order filter, third order filter, fourth order filter? What is the necessity go to use a different order filters? First introducing, why you are introducing different order filters, and why are you using only that respective filter? Everything we discuss in active filters. Sir, is it clear?
Yes, sir.
Okay. Now, first I will represent. We go to frequency response of this. See, now let us, the current is I1 and this current is IC. So here, this voltage at this point is 0 volts and current entering into this also 0 amperes. Now applying KCL at this point. By applying KCL, we can write I1 entering is equal to IC leaving plus 0. So now I1 is written as Vi minus 0 by R1. R1 equal to IC. Current through the capacitor is current through the capacitor is 1 by C into dV by dt. That is the current through the capacitor. So now it is a 1 by Cf into dV by dt. That means d by dt of V. V means voltage at this point minus voltage at this point. Here voltage is 0 volts. Here voltage is V output. V output plus 0 amperes. So now from this we can write Vi is equal Vi by R1 into Cf is equal to minus dV output by dt. So next one is now from this we can write output equal to minus, just integrating both sides simply, okay, or directly dV naught equal to minus Vi by R1 Cf into dt. Just integrating both sides, then V naught equal to minus integral Vi into dt. So this is constant 1 by R1 Cf. So V output is directly proportional to integral of Vi dt. So there is a negative polarity. The negative polarity represents
Integration.
phase shift. Phase shift. It represents phase shift, 180 degrees phase shift, because you are applying input signal at inverting terminal. If you are applying input at non-inverting terminal, at output you get the positive. Okay, so you are applying input terminal at negative. So because of that, output is phase shifted. Okay. Next one. So now is it clear, sir?
Yes, sir.
Now, so next we go to frequency response of this. ठीक है और नहीं लगा हेल्थ लेगा now see I'm going to frequency response. Sir, can I rough this one? Sir, can I rough all this?
You can, sir.
Thank you. Now see, basically this is it is in the form of inverting amplifier or not? So once it is in the form of inverting, we can apply directly inverting concept on this. Okay. So what is inverting concept? Closed loop gain is minus RF by R1. So now the closed loop gain of this one is minus RF by R1. But in case of resistor, here we have capacitor. Now that's why I'm representing R by Z minus ZF by Z1. Now here ZF is reactance of the capacitor, that is 1 by C into just a minute. 1 by I will take in the form of S domain. Okay, later we can take S equal to J omega if required. Z equal to 1 by S CF and Z1 equal to R1. So now it is closed loop gain. Also we called it as transfer function. H of S it is the form. Equal to minus 1 by SCF
R1
to R. Okay, now I am taking 1 by R1 CF as F omega A I am taking. Let us assume. Okay, and at the same time I'm taking yes, okay, and I am taking at the same time I will take S is equal to J omega. Now substitute values. Closed loop gain is or transfer function is equal to minus 1 by R1 CF is nothing but omega A by omega J omega. So we can write this is minus 1 by J became J omega A by omega, or you can also write J into omega means 2 pi F, so F A by F. Now series. Now I am taking the magnitude. Just a minute, sir. Now closed loop gain or H of J omega, magnitude of that one is F A by F Sir, just 1 minute, sir. Here they are doing sanitization. Just wait for 2 minutes. Okay, no problem, no problem. There it goes. అక్కడ కూడా. Yes. Now, so this is FA by F. Now I am taking the different values. Different values I am taking here. So let I am taking first F is equal to 0. At F equal to 0, H of j omega became infinity. At F equal to Fa, it became 1. And at F is equal to infinity, something by infinity, 0. It became 0. So now if I plot this, our plot became like this. This is a magnitude of h of s or closed loop gain, both are the same. And this is the f. At 3 different values we plot it. F equal to 0, f equal to 0, f equal to fa, equal to somewhere in infinity. Now, see at f equal to 0 it is infinity. At f equal to fa, it became 1. It became 1. Became 1. At f equal to infinity, it became 0. So, okay. Okay. This is the plot. There is one drawback in this. That is, at low frequencies, its closed loop gain or transfer function is infinity. That means at low frequencies, it is not stable. The purpose of giving feedback to your system is to provide stability to that. Providing stability to your system in this sense, the output values should not be infinity. That means should be known value or should be a definable or representable value. Here it is infinity. That means it is going to instability. It leads to instability of your system. So that is the drawback in this. So at low frequencies, your system, your integrator is not stable. So that is the problem in this. Sir, is it okay? And sometimes in last year IES they asked one question. Calculate the unit, see, listen carefully, sir. Unit gain frequency of an integrator. Unit gain frequency of an integrator. See this. At f equal to fa, your closed loop gain is nothing but a h of this. This is nothing but a closed loop gain. This is going to be 1 at f equal to fa. And fa value is, so f is equal to fa. And fa is omega a, sorry. Just a minute. So f is equal to, you are writing 1 by 2 pi. Sorry, just a minute. So our basic, I will start from basic. So we know omega is equal to 2 pi f. Just follow this. Now you are taking this is fa. Just add a to this. Now fa is nothing but a omega a by 2 pi. So we know omega 1 by r1 into cf is the omega. Okay. Now just add 2 pi to this. Now 2 pi into r1 cf is the unit gain frequency value of integrator. Please all of you take a note of this one, sir. Unit gain frequency of an integrator is 1 by 2 pi r1 cf. 1 by 2 pi r1 cf. Okay, sir. Sir, is it okay, all of you? So it leads to instability. It means unstable. Your system is unstable. Your system is not stable. It leads to instability of your system. Now that you need to provide a stability to your system. So whatever the integrator just before we are discussing here, so now this integrator is unstable and this is the ideal integrator. So for stability, what we are going to do, what I want to do for increasing the stability. Any suggestions from your side? So the problem is it is not stable. That is the problem. Okay. So I want to add this, increase the stability of this. Increasing stability in this sense, closed loop gain should not be infinity. That is the point. Closed loop gain should not be infinity. Closed loop gain should not be infinity. That is the meaning of providing stability to your system. What I want to do. Any suggestions from your side? Any suggestions? What, sir? Any suggestions? Just think of it. Just think once. ಮನ್ಯಾಗ ಕಾಲ್ ಬೇನ್ ಬರಲ್ಲ. Hello? Hello? Any suggestion from your side? Okay. So closed loop gain became infinity na, for this. That means this is not stable. So I want to increase its stability. Then any suggestion from your side? Any modifications are you suggesting to this circuit?
Resistance parallel to capacitor.
Where? For CF.
CF.
So, for CF, you are saying. So according to your suggestion, one resistor should be placed parallel to that capacitor, or one capacitor parallel to this. Or series to this. See, okay, what you said was right, but now I will explain in detail. Now, see, this is fine. What we said was given in a proper way. It is unstable at low frequency. It became infinity. That means it is an unstable system. Fine. But in circuit point of view, how can I understand that instability? Circuit point of view. Say this. That problem rises at low frequency. Yes or no? At f equal to 0 at low frequency, that problem of instability taken place. Yes or no? Yes or no?
Yes, sir.
So at low frequency, what about your capacitor? Open circuit. So at low frequencies, the circuit became like this. So this is your circuit. Now this is there is no closed loop. In this circuit, there is no closed loop. It is open circuited. Now output is either plus or minus V saturation, not the integration of input. So your system is entering into open loop mode. That is the problem. That's why your system is losing its stability at that point. Okay. If even though your capacitor is open, if I add one resistor to that like this, one resistor like this, then even though your capacitor is open circuited at that point, at that time, due to this resistor feedback continues, then output is minus RF by R1 into Vi, just inverting amplifier. Yes or no? Sir, sir, is it okay? Hello? Now, the same thing I am doing.
Okay, sir.
So, because of that only, here you are adding one resistor. So, just that's it. Now this is practical integrator. This is the circuit for practical integrator. So now there is no instability in this. So previously unstable problem, stability issue. Now there is no stability problem in this. So is it okay?
Okay, sir.
So this is your circuit diagram. Circuit diagram of practical integrator. Okay, before going to that, just a minute, I will go back to this waveforms. See, for example, sometimes they will give some waveform and they will ask what is the output waveform. For differentiator and for integrator, they will ask same thing. Simple. We know one thing. Just check this waveform. It is a square wave. From here to here, it is a constant value. What is the integration of constant? Integral constant. What is the integral constant? 0. Sorry. What is integral of constant?
X.
2t. Integral constant is t. But next integral of x is x squared. Similarly, d by dt of 2 is 0. Okay. Differentiation of x is 1. Okay, now say this. This is a constant value. Okay. It is integrator. Integral constant is t, linear. So this is a inverter. Input applying at negative terminal. That's why it is like this. Linear waveform. We call it as a spike. Okay, based on the R and C values, this is changing. The spike is changing. Similarly, this is a linear triangular. This is x, integral x. X square by 2. Okay, sir. So you get parabola, not this one, not this one. This is for, say, for a differentiator, this is the output. These are the waveforms for differentiator. Okay. This is for integrator. This is for sine, we have cosine. For sinusoidal, cosine wave. For cosine, sinusoidal. Because integration of sine is cosine, differentiation of sine, cosine also sine. Sir, is it okay? Just whatever the regular cosine and sine concepts, you apply that one. That's enough. Okay. So now I am going to this practical integrator. Okay. Now, so before going to this, just keep one term in your mind. Already we defined omega A. It is 1 by R1 CF. Now, So this is like inverting. Now similar to previous case, I am writing here is so here I am writing is closed loop gain is minus ZF by Z1. So Z1 is R1 and ZF is parallel combination of these
RF
two. That
parallel.
means RF into 1 by SCF by RF plus 1 by SCF. So now ZF is, so it is RF by 1 plus S into RF into CF. This is the CF. ZF. Now substituting that minus ZF means RF by 1 plus S into RF CF. CF by Z1. Z1 means R1. So by R1. So now we can write it as minus RF by R1 1 by 1 plus S into RF into CF. Now I am taking let RF CF equal to 1 by omega B and S is equal to J omega. Now it became minus RF by R1 by 1 plus S is equal to J omega, J into omega by RF CF equal to 1 by omega. This is the plot. So now closed loop. Now magnitude of, I am taking the magnitude. So if you take the magnitude of this, so magnitude of closed loop gain is RF by R1 by square root of 1 plus omega by omega B whole square. Okay, now let us take different values. Omega equal to 0, omega equal to omega B, and omega equal to infinity. So for this omega equal to 0, it is 0 RF by R1. So closed loop gain is RF by R1. For this omega equal to omega B, something by root 2, RF by R1 by root 2. Omega equal to infinity, 1 plus infinity is infinity, something by infinity became 0. So now the plot became like this. So it is closed loop gain and it is a frequency. 0 frequency, it is a omega B. So somewhere in between 0 it is. Now this is RF by R. RF by R. Now so at 0 frequency its gain is RF by R1. At omega equal to omega B, sorry, so this is a, I'm taking it as a omega B. Hello? Hello, madam.
Sir,
నడుస్తుంది జరుగుతుంది మేడం. హలో, ఏం నాకు తెలియదు మేడం, నేను దీంట్లో ఉన్నాను. Yes, ma'am. Recording is going on. Recording is going on. Yes. Yeah. Now it is. So at omega equal to, sir, you can take it as omega or f, both are same, not an issue. One is angular frequency, other one is a linear frequency. So now it is Rf by R1 by root 2 at omega equal to omega b. So now it is going decreasing like this. Finally it becomes this is, now we called it as a band. This is called band. See, here it never reaches the infinity. It never reaches the infinity. That means now it became stable. Now it became stable. Okay. Now sometimes you have to go for designing of an integrator. Okay. Designing of an integrator. How to design an integrator. Okay, all of you write down these points. How to design an integrator. How to design an integrator. Serious. See, this is the frequency plot what we get. This is the frequency plot what we get for an integrator. Okay. Now, they will ask design a practical integrator circuit. Design a practical integrator circuit to integrate frequencies up to some 2 kHz or 4 kHz something. Okay, so the frequency what they given is maximum frequency. Maximum frequency. Okay, and here we defined previous two frequencies. One is FA, other one is FB we given. FA is 1 by R1 CF and FB is 1 by 2 pi here. 1 by 2 pi into R CF. So first you should know one thing. In all the case, you have to assume the capacitance. C value you have to be assumed 0.1 or 0.01 microfarads. Or sometimes they will provide that value to you in exams. Sometimes they will provide that value to you. Okay, now here practically this maximum frequency is equal to FA value. Whatever the FA value here we have, that maximum frequency is nothing but a FA value. And FB is FA by 10 times generally. Generally we take FB is FA by 10 times or F maximum by 10 times. So that means in this problem, for example, I want to design an integrator, practical integrator with that value. Designing in this sense, in our circuit diagram, we use R1, RF, CF, three parameters, three elements with op amp. So op amp you can use it, 7.4 on op amp you can go for it, it's not an issue. and CF we are assuming 0.01. Now we need R1 and RF. So they're given 2 kHz. By substituting that 2 kHz here, so we know this one, and we assumed this. From this you get the R1 value. Similarly, from this you get the RF value. Now FB became here FA by 10. That means a 2K by 10. 0.2 kHz. So from this you get the RF value. That is the designing. So whatever the frequency they are giving, that is FA equal to FA. Sir, are you clear about this integrator?
Yes, sir.
So that is the picture about complete integrator. Now we go to the next one is a differentiator. Now you may ask one thing, sir, how can we go for differentiator? See, basically you are observing or not, basic inverting amplifier they taken, in that they replace RF initially by capacitor R1 as it is, that is integrator. Now they interchange the terminals. R1 replaced by C1. Now they keep RF as usual. Now this is a differentiator. Okay. Now same way, same problem, sir. I'm going to take the directly. It is okay. See, let us take it as I1. It is IF 0 volts. This current is 0. So applying KCL, I1 is equal to IF. I1 is nothing but a VI minus 0 by 1 by SC. Sorry, just a minute. Okay, we are not taking the frequency response. Current through the capacitor is 1 by C into dV by dt. D by dt of C1 minus 0. Sorry. dV so dV by, so it is VI minus 0 is equal to IF is 0 minus V output by RF. Now from this, so we can write minus V output equal to sorry sir, it is just 10 minutes. So this is C sir, we are writing current now for capacitor, not for inductor. C it is C1. So C1 into RF into dVi by dt. So output is directly proportional to dVi by dt. So this is differentiator. Now at the same time I'm going to frequency response of this. Okay, now frequency response. Sir, we in detail we done on integrator, sir. Same one, nothing is different. See, in this I1 is equal to IF. I1 is current through this, so that is VI minus 0 by 1 by SC. 1 by SC1 is equal to 0 minus V output by RF. So closed loop gain is V output by V input. It is minus SC1 into RF. So let I am taking omega A is 1 by R1 RF into C1 and S is equal to J omega. Now just substitute that values. substitute that values. Now closed loop gain became minus j omega by omega a. So magnitude is omega by omega. So here also same thing. At omega equal to 0, closed loop gain became 0. At omega equal to omega a, closed loop a became 1. And omega equal to infinity, closed loop gain became infinity. See this same problem arises once again. At high frequencies, so here omega is infinity. Here closed loop gain became infinity. Again our closed loop gain became infinity. That means your system is not stable at high frequencies. Okay. Now your plot became like this. You get your plot like this. Like this. So at high frequencies, no stability. Okay. Sir, are you clear about this?
Okay, sir.
Hello? Okay. Now,
Okay.
so how to solve this problem? In circuit point of view, what is that problem? How can I analyze that problem? High frequency, F equal to infinity. Let us. So for F equal to infinity, your capacitor became open circuited. Sorry, short circuited. At high frequencies, capacitor became short circuited. Once it's short circuited, input voltage shorted to this voltage. But voltage at this point is 0 volts. 0 volts. Okay. Now, input voltage shorted to 0 volts. So input voltage became 0 volts. So at output you get 0. So that is the problem here. Even though you are applying input, it is not recognized by your op-amp at high frequencies. Okay. So to differentiate these two, I am going to adding one resistor. If I place a resistor, then I can easily differentiate voltage at this point and voltage at this point. That is what I am going to doing in next level. Say this in this level. Just I am adding one resistor here. This is a practical differentiator. Now I'm going to close the loop gain of this circuit. See, so now closed loop gain is you can write this closed loop gain for this one is so closed loop gain is minus ZF by Z1. So here ZF is nothing but RF and Z1 is series combination of R1 S and C1. That means R1 plus 1 by SC1. That is. Now substitute those two here. Next minus RF by Z1 means R1 plus 1 by SC1. Now I am taking R1 common in this denominator. Now it is minus RF by R1 by 1 plus 1 by SC1. SC1 R. Okay. Now let I am taking omega B became 1 by R1 C1. And S is equal to J omega. So now you can write this one as now H of J omega transfer function is minus RF by R1 by 1 plus omega B by J omega. So it is minus RF by R1 by 1 minus J omega B by omega. Just take the magnitude. So minus RF by R1 by square root of 1 plus omega B by omega whole square. So this is closed loop gain, sir. Sir, compared to integrator, I'm taking a little bit fast here because already we done in multi-analysis on integrator. Okay. Now, I'm going to plot this. So this is magnitude we are taking. That's why there is no negative here. It is became positive. So now, at omega equal to 0, omega equal to omega b, at omega equal to infinity. So at omega equal to 0, something by 0, see here, something by 0, infinity. 1 plus infinity, infinity, something by infinity, 0. Now, our closed loop gain became, our transfer function became 0 here. At f equal to omega b, it became rf by r1 by root 2. By root 2. So at omega equal to infinity, something by infinity became 0. 1 plus 0 is 0. Sorry, 1 plus 0 is 1, root 1. So rf by r1 max. So now the plot became like this. It is closed loop gain. It is frequency. Either you can take omega or omega, it's not an issue. This is 0. So 0 omega b, it is infinity. This is the maximum value, RF by R. Now, so at here it is 0 initially. So by increasing frequency, it is also increasing. And at omega equal to omega b, it is RF by R1 by root 2. And omega equal to infinity, RF by R1. So infinity, it is RF by R1. Now, from this slowly, like this. So at this point, this is, it is RF by R1 by root 2. So this is the practical differentiator. Previous case, in the designing point of view, we taken the maximum frequency is equal to FA. Now they will ask, in this case they will ask the minimum frequency. This minimum frequency is FB or omega B. So design an differentiator to differentiate a minimum frequency of 2 kHz. 2 kHz. Now you can take this one is FP. Okay. Now assume the free capacitor similar way, 0.01 or 0.1 microfarad. Okay. And from this FB you get the value of R1. R1 from the knowledge of FA you get the value of RF. Same procedure, sir. Whatever the procedure we followed in differentiator, in integrator, here also we are following the same procedure. Okay, sir. This is about your integrator and differentiator. Next one is, so we have two more applications in linear. Today we complete those two. Voltage to current and current to voltage converter. In voltage to current, we have two types. So here we take note. We have two types of voltage to current converter. Two types of voltage to current converter. First one is a floating load. Floating load. floating load. Second one is grounded load. So this is the load, your load is floating here. So this is the floating load voltage to current converter. Okay, now that means here my intention is whatever the input voltage here I have, I want to convert this input voltage in terms of load current passing through this load resistor. Load resistor. That is my intention. Now let us, I am assuming this is current I1. This current is 0, we know that. Applying KCL here. Now the voltage VI, so same voltage VI takes place here. Applying KCL here. Now I1 is entering, is equal to 0 is leaving, plus load current IL is also leaving. Okay. Now load current is I1 finally. Now I1 is nothing but a voltage at this point minus voltage at this point by R. That means 0 minus VI by R. So which is minus VI by R. Therefore, load current is minus VI by R. See this? Now input voltage, this is our input voltage. I converted this input voltage into output current or load current. Okay, so this is the floating load voltage to current converter. Next one is a grounded load. Grounded load. So this is the grounded load voltage to current converter. Same thing here also. My intention is to convert this input voltage into load current. This is the load resistor here we have. Now let us take this is the load current. Load current. Okay. Now let us, I am taking, this is current I1 and this is current I2. And voltage at this point and voltage at this point, both are same voltages. Now I am assuming that voltages are, let us, Vx and it is also Vx because both are same voltages. Voltage at inverting equal to voltage at non-inverting. In this, negative feedback is exist, so you can apply that. Okay. Now I am applying KCL at this node. So at this node. Now IL is leaving, I1 is entering, I2 also entering. So therefore IL is equal to I1 plus I2. So I1 is nothing but a voltage at this point minus voltage at this point by R. So Vs minus Vx by R plus here R is V output minus Vx by R. By R. Now this is Vs plus V0 minus 2Vx by R. That is the equation for that. Okay. Now so you need a relation between V0 and Vx. See this? In this circuit, once you set this is the voltage Vx, once you set this is voltage Vx, now this is a non-inverting amplifier, voltage at non-inverting terminal is Vx. Now I can write easily output voltage is equal to 1 plus Rf by R1. At Rf I have R1. At Rf I have R1. by, in place of R1, R1 itself, R1 into Px, Px. So this is nothing but a 1 plus, this both are same, it is 2Vx. Just to substitute this 2Vx in place of V naught here. So now we can write load current IL is equal to Vs plus V naught minus, sorry, Vx is already calculated 2Vx, V naught is 2Vx, 2Vx minus 2Vx by L. So both will cancel. Therefore, load current is Vs by Rn. See here, your input voltage converted into output load current. That is the voltage to current converter. You may ask one thing, sir, how can we identify this many number of circuits we have? How can we identify the given circuit is particular related to belongs to this particular? See, just I am giving the name to that circuit based on its relation between input and output only. Okay, whatever the circuit they given, just apply inverting and non-inverting concepts on that. Deduce a relation between input and output. Based on that relation, just give name to that circuit. Why I am using the term here is in gate examinations, sometimes they will give circuit and they will ask the identify the following circuit. It is an integrator, differentiator, voltage to current converter, or current to voltage converter. They will ask like that. In that case, to answer those questions effectively, you should be thorough with that type of method also. You can practice that one also. These are the voltage to current converters, two circuits. Now I am going to current to voltage converter. This is your current to voltage converter. Okay, just check how it is a current to voltage converter. First of all, here voltage is 0 volts. So 0 volts here also. Once 0 volts, now the voltage at this point also 0 volts. Now it is grounded also 0 volts. Due to the same potential, current through this one is 0 amperes. Are you clear about this? Sir, are you clear about this? Now, let us take this is current IF and this is the current IS from this side IS. Now I am applying KCL at this node. So IS is equal to IF. IS equal to IF. So IS is IF means voltage at this point minus voltage at this point by R. Voltage at this point 0, here V naught by R. So now from this I am writing output is equal to minus IS into RF. See this, just input current is converted into output voltage. You are applying signal at input side in the form of current. At output you are getting that one in the form of voltage. Okay, so that is a current to voltage converter. Okay, so that is, these are the voltage to current and current to voltage converters. Next I am going to instrumentation amplifier. So this is instrumentation amplifier. So just a minute. So that is RD is equal to R plus R minus delta R, plus R minus delta R. Okay. plus or minus delta R. See, this is instrumentation amplifier. First of all, what is the necessity to go for instrumentation amplifier? See, mostly this instrumentation amplifier is using in sensors. Sensor is a device to sense the variation in particular parameter. In the sensing time, at the time of sensing, it should sense a variation in even 0.1 millivolt of change, also a variable voltage. Now initial voltage is 1 volt. Now next level voltage is 1.001 volt. Now there is a change. The change is due to some property change or property variation in a particular material or some device or some element. Okay, you can't neglect that change 0.001. Okay, so to identify that small voltage of 0.001, okay, if I am using a resistors, that 0.001 volt drop takes place across the resistor. Finally, at output, you get nothing. Okay, that type of problems rises here. Okay, so for that reason, to identify a small changes, and after identifying the small changes, that signal has to be amplified to increase the strength of that signal, because that amplified signal is going to drive some meter. So 0.001 volt of value is not going to drive any, not producing any deflection in meter. So to produce a minimum deflection in meter, the signal has to be amplified. For that reason, here we are using instrumentation amplifier. So this is the instrumentation amplifier here we are using. Now let us see this, how it is working. First of all, this part, now let us, I am taking some voltage. Let us take this voltage. Let us take this voltage is VA and this voltage is VB. Basically this is voltage follower. This is also voltage follower. So this is VA means it is VA. Here also voltage VA. So the same voltage VA here. Now same voltage VA here. Similarly, it is VB. It is also VB. And this part of the circuit is subtractor. Now from this part we can write output is R2 by R1 into at positive terminal we have VB minus VA minus VB. This is the equation. Now you need to get the value of VA and VB from the circuit. Now from this I am writing, okay, I am assuming, let us for my easy understanding I am assuming RA equal to RB equal to RC is equal to RD is equal to a resistance R. Let us assume. Now I am writing VA is VDC into, let us take VDC, I am taking V into voltage division, sir, RB by RC plus RB. RB by RC plus RB. Now it is V into, because RA equal to RB equal to RC equal to RD equal to R we are saying. So it is simply V by 2. Similarly, I am taking VB is V into RA by RA plus RD. Now we can write this is V into RA by RA plus RD is, sir, now no RD sir here, because we are taking RD is R plus or minus delta R. R plus or minus delta R. Delta R is the small change in resistance. Now my intention here is to convert a small change in delta R, the small change in resistance delta R, into change in output voltage, proportional change in output voltage. That is my intention here. Okay, now see, now this is your VB, sir. Now final value of VB is V into, this is R by R plus R plus R minus delta R. Okay, now I'm taking this is V by, it is R gets cancelled, it is 2 plus R minus delta R by R. That is VB. So your final output equation is, your final output voltage is R2 by R1 into V. So what is that, VB or VA? Okay, VA minus VB. VA minus VB. Substitute values. R2 by R1 into VA is V by 2 minus VB is V by 2 plus R minus delta R by R. Just to simplify this, R2 by R1 into, taking V common, now it is 2 plus R minus delta R by R minus 2 by 2 into 2 plus R minus delta R by R. So now output is V into R2 by R1 into, see here, this 2 and this 2 gets cancelled. It is delta R by R by 2 into 2, 4 plus R minus 2 delta R by R. See, delta R is very small value compared to R. So delta R by R is very small compared to 4. So here delta R by R is much smaller compared to 4. So we can neglect that value. Therefore, now we can write 4 plus R minus 2 delta R by R is written as approximately 4. Therefore, output voltage is V into R2 by R1 into delta R by R into 1 by 4. 1 by. In this is constant, this is constant, this is also constant. So your output is directly proportional to change in resistance. That is the instrumentation amplifier. See clearly here, output is changing with respect to change in input, change in resistance. Okay, sir? Sir, is it okay, all of you?
Okay, sir.
Now, previously they given this problem in exam. Calculate the change in differential gain. Let us take this is a V1 and it is V2. They asked the question in exam, what is the differential gain of this amplifier? Differential gain in this sense, differential gain means AD, which is output by differential input voltage, VD. Differential input voltage VD is V2 minus V1. Here, see this. This is V1. Now it is also V1. It is also V1. It is V2. Voltage follower it is. So it is V2. It is V2. Simple. This is nothing but a subtractor. To get a just to make a confusion to you, they added two voltage follower circuits to you. Therefore, AD is sorry. Now it is output voltage is simply from subtractor R2 by R1 into V2 minus V1. So differential gain is V0 by V2 minus V1, which is R2 by R. Simple. That is the gain. Okay, sir. Sir, is it okay? So that is the circuit. And another construction is there for differential amplifier, instrumentation amplifier. So that is this type of this is also comes under that. This is also comes under that. This type of structure also present at input side. Okay, I will give this circuit in the next class. We discuss about this. See, next one is log amplifier. In case of RF, I replace the diode. Just see, sir. Here, my intention is to give the importance of inverting and non-inverting amplifier. Just I replace with the transistor in place of RF. Next, in place of R1, I replace the diode. In place of R1, I replace the transistor. Okay, so this is next one is log amplifiers, anti-log amplifier. This is analog multiplier. So if you want to do the multiplication, division, square root of the signal, okay, to do all those things, we use this. So this is about your today's class, sir. So next session, we go to the inverting, log amplifiers, anti-log amplifier. Okay, from that voltage multipliers, all those things we discuss. Sir, any doubts? Sir, any doubts to anyone? Sir, can you please? Any doubts? Any doubts, sir?
No, sir.
Sir, whatever the way I explained is not important. You are asking doubts or not, that is very, very important. You have to ask the doubts because from that only I know where you are. Okay, what is your way of thinking? Okay, based on that, I will clarify your doubt. At the time of discussing integrator, one student asked the doubt, sir, by seeing the circuit itself, how can we identify? So if you know integrator is a low pass filter, differentiator is a high pass filter, from there we are going to back tracing that. First getting the which type of filter it is. After that, it is integrator or differentiator. Okay, like that. If you are asking doubts in your point of view, I will clarify all those doubts. And as a subject also, I will explain in that aspect. Okay, that is very helpful to you. Okay, sir. Thank you, sir. Thank you very much. Thanks to one and all. Madam. 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 Madam, okay, madam.